Thank you. Thanks to the committee for this opportunity to educate you on my concerns. My background is as a molecular and cell biologist. I have a bachelor's and master's degree in molecular biophysics and biochemistry from Yale, a PhD in biology from MIT, several years of postdoctoral training, and then I came to Berkeley in 1995 as a professor. So I've spent the past 14 years teaching molecular and cell biology, and in particular teaching chromosome biology, DNA damage and repair, and cancer biology. My laboratory does primary research on that, and I teach it. So my presentation, what I will tell you, has to do with what methylating agents, such as methyl iodide, what impact they have on our genetic code and on the function of our cells. And I submit, Assemblymember Berryhill, that it's never too early for a little bit of education. So I have a handout, but actually I want you to just put it down because it contains the literature references that are the support for what I'll tell you. You just have to listen to me. You know that there are 4 units in our genetic code. There are 4 building blocks. And these 4 building blocks have to be replicated and replicated and replicated. And so of these 4 building blocks, 2 of them are sensitive to the kind of damage that these methylating agents cause. Chemotherapy, several chemotherapy agents act by methylating, so they're very toxic, and they attack the genetic code of any replicating cell. So all the replicating cells in our body will get attacked by these methylating agents, and there's quite a lot of research on methyl iodide. There's 3 types of damage that are known to occur from methyl iodide, which is great because we can then track down what will happen to those kinds of damage. They damage 2 of the 4 units of the code. So there are 3 general responses to DNA damage in our cells. We damage our DNA just by eating food. Low levels of DNA damage are repaired. We have many different mechanisms to repair these damage. So some types of methylation will be repaired. If the damage load is very high, like in the chemotherapy case, cells in multicellular organisms like us, they choose to die, they commit suicide to save the greater organism. So that's the principle of chemotherapy. You take a high dose of something that overwhelms the repair system, and the cells die. But there's a third consequence, which is genome mutation. So certain kinds of mutagens are not just toxic in the short term, in the sense of causing damage or causing cell death, but they're mutagens in the sense that they change the code. And these are particularly frightening kinds of mutagens, particularly for long-lived organisms such as us, because the way that we get cancer, the way that we get disease is cumulative. Every damage that changes the code, one damage may not do it, but there's a multi-hit theory of cancer where 4 mutations or 5 mutations combine together to give you cancer. So the toxicity you can see short term. Somebody's poisoned, they go to the hospital, all the cells have killed themselves, they regrow that tissue. But this toxicity from changing the code is far more difficult to evaluate. So one of the 3 kinds of damage that's caused by methyl iodide is something called 0,6-methylguanine that you don't need to know. But this is a particularly insidious form of damage. In fact, most bacterial organisms have evolved pathways we don't have to fix this one thing in specific because it changes the code. There's a reason that it's so deleterious is that the DNA that's modified in this particular way, it looks like a normal part of the code, but actually it doesn't look like itself. It looks like one of the other 4. So if there's 4 units in the code, the G doesn't look like a G anymore. The G now looks like an A. So when it goes to be copied, you've actually changed the code. It can be repaired, but if it's not repaired, it changes the code in a permanent way. And these permanent damages add up to cause high carcinogenesis. Now, I also want to add a note that all of the studies in the literature that estimate carcinogenicity or toxicity in terms of long-term genetic stability, they're done on mice because there's morally less obligation to killing the mice. But mice live for 2 years. Mice do not get the spectrum of cancers that we get. So, in fact, all of those studies that are done on model systems that are short-lived underestimate the carcinogenicity of these compounds. And so you may not, I mean, I think that we have to be particularly worried about compounds where we can't, in a short-term manner, assess the risk. Finally, I just want to finish by saying that, as Neil commented at UC Davis, at UC Berkeley, we are not allowed to dispose of this compound to the environment in any manner. It is a zero-release compound. It is a Class C toxin, way higher than all the radioactivity that we use. We are not allowed to dispose of this into the environment because of the toxicity and because of its carcinogenicity. So if I wanted to use this in my lab, as if Neil wanted to use it in his lab, we would not be allowed to even dilute it infinitely and dump it down the sink. And if I proposed an application to use it in my lab, I would do a stack of paperwork, and this is relevant here too, about why I absolutely had to use that compound. And if, like you're saying, the habit is to use soil fumigants, I would actually have to say why I need to grow my strawberry with a soil fumigant. Are there alternate ways to grow strawberries? I would have to do a 10-year search of all the published literature to provide the rationale for why I wasn't asking a different question, not which soil fumigant to use, but how to grow. Does growing strawberries need a soil fumigant? And so that's the level of burden that would be placed on me in an academic setting. And this is just for information. I obviously, am not a member of a review board, but I'm saying that this is the kind of standard, the concern that UC Berkeley has, and the regulations there are tight on methyl iodide.
Thank you, Dr. Collins. Appreciate your testimony.